Welcome back to the ChemDoctor, and this is the third video in the playlist that deals with solubility equilibria. And what we're going to tackle in this presentation is we're going to calculate the solubility of sparingly soluble salt in the presence of a common ion. All right, so let's look at the problem directly. We're going to calculate the solubility of silver chromate in 0.1 molar silver nitrate, where the equilibrium constant KSP is 9 times 10 to the minus 12th. All right, so the first thing that I want to do is I want in all these videos for us to make connections. So the first thing that we're going to do is translate the name of this compound into its formula. So silver chromate. All right, so the chromate ion is CrO4 minus 2, and silver ion is part of what I call the triad, and that includes silver Ag plus 1, zinc plus 2, and aluminum Al plus 3. So the silver is Ag plus 1, Ag plus. So now when we look at these two compounds, you can use drop charge to figure out the formula if that's what you want to do. I think if you're in an advanced level chemistry class, though, it's really important for you to understand charge balance, and so you need to look at the two ions and figure out how many of each one that you need so that the final compound has a net charge of 0 on it. And since the chromate is minus 2, we're going to need 2 silver ions in order to balance that charge. So the formula here is going to be Ag2 CrO4. And then if we look at the solution that's being combined with this material, it's silver nitrate. And again, the silver is plus 1, and nitrate is one of the what I call the 24 polyanions that you should know by heart, and it's NO3 minus. So the compound in this case is AgNO3. All right, and the importance of something else about the importance of the nitrate is realizing that all nitrates are soluble. So silver nitrate is fully soluble in water. So I'm going to put an arrow here, and I'll just make that notation. So it's fully soluble, whereas the silver chromate is a sparingly soluble salt whose KSP is 9 times 10 to the minus 12th. Now, I want to give you the setup of this problem because I think it's really important in your own mind to have a way of looking at this that makes this understandable. So in the common ion problem, here's what the deal is. So I'm going to draw a picture of a beaker, and in the bottom of this beaker I'm going to add the powder, which is the silver chromate, and it's going to be a reddish brown powder. All right, and then what we're going to do is layer above that the silver nitrate solution. Excuse me. So I'm going to do that this way. I'll just show this blue for the liquid water, and then we're layering in silver nitrate. So this is actually 0.1 molar silver ion, and you can put the nitrate in here if you want, but it has no bearing on the equilibrium position of this reaction because it's not included in the equilibria. So here's what I mean. If we write now the equation for this equilibrium, it's silver chromate, okay, solid, which is in equilibrium with its two ions, the silver and the chromate. Four minus 2. All right. Now, so let's go back to the setup of the problem. So the way to think about this is you have this beaker. You layer in the silver chromate, which is a powder or, a solid crystal. And then over the top of that, we layer in the 0.1 molar silver nitrate, of which the silver is fully soluble. So what we have here is a 0.1 molar solution of silver ion sitting on top of this solid, and then we're going to allow the system to come to equilibrium, and that's the part that you need to understand. We're going to let this thing shift to equilibrium. So if we set up our ICE table, and again I just use an arbitrary letter here as a placeholder for the solid, because remember this is a heterogeneous equilibrium, and the solid material that's here, all right, is its individual density or concentration is constant throughout this entire process. So in other words, even though the system shifts to equilibrium, the amount of dissolved ion is extremely small by comparison to the solid. And so as long as there's solid present in here, the individual density of that material never changes, even though some of it, a very small amount of it, dissolves into the solution. All right, and coming back to the ICE table or the box, we can set up what our situation looks like before equilibrium. All right, and before equilibrium, we've got the solid sitting in the bottom of the beaker. All right, the chromate is 0. There is none of that to begin with, because remember, we put the solid in here, then we layer the solution in over the top of it. However, with the silver, there's already a 0.1 molar solution of the silver ion present before we reach equilibrium. Now, after the system makes its shift, all right, the solid is going to decrease by some factor x, right? And this x thing right here is in fact what we call the solubility. So when we use that word, that's what we're talking about. The solubility of this compound, the amount of this material that actually dissolves to a molarity concentration. And then as this thing shifts to equilibrium, and then we're shifting to the right, and I just want to make sure that the viewers understand why I know it's going to shift to the right. And the reason is, thinking back to Le Chatelier's principle, is that before any reaction occurs, see, there's 0 of chromate, and the system has to shift to fill that hole. And so it has to shift to the right. There's no way you can shift to the left because there's an absence of the chromate ion altogether at the beginning. All right? So we're shifting to the right to get to equilibrium. So this is going to be 0.1 molar for the silver, okay, plus 2x, and then the chromate is going to be x. Now, we can set up our equilibrium expression, and to be clear about what that looks like, the KSP is going to be equal to, okay, the concentration of silver ion raised to the second power times the chromate, which is just raised to the first power because the coefficient here for the chromate is 1. All right, now let's go ahead and set up our equilibrium expression for the common ion situation. So the KSP is 9 times 10 to the minus 12th, which is equal to, all right, so the silver expression is going to be 0.1 molar plus 2x, and that quantity is squared. And then we have that times the chromate, which is just x. Now, when you look at this, you can see we got an issue here, because if we were to go ahead and carry out the algebra, we're going to end up with a cubed expression. However, going back to what we learned earlier in earlier videos dealing with equilibriums where the equilibrium constant is small, we have an advantage here. Since k is 10 to the minus 12th, we can actually neglect the sum in this equation. So we can neglect the 2x that's in the sum, and that will reduce our expression to 0.1 molar times x. Now, the one thing that you've got to be careful about when we neglect the x, and we're going to be okay in this problem because the equilibrium expression is really, really small. But in these solubility problems, just so you know, and I'm going to make a notation here so that you remember it, when you get up into k expressions that are that are somewhere on the order of around 1 times 10 to the minus fifth, you need to watch out for this assumption, because the x value that we eventually solve for may be comparably large to the 2x value, and if that's the case, then you cannot make this assumption, and at that point you better have a really good calculator, or hopefully you can abandon the problem, because it becomes too complicated to try and solve for. So going ahead and finishing, then we find that x is equal to 9 times 10 to the minus 10th molar. So this is the solubility of the silver chromate. This is the x value, and I'm going to move this up here so it's very clear. So this is 9 times 10 to the minus 10th for that x value. Now, here's what I meant when I was talking about neglecting the x. The x value here is 10 to the minus 10th, and you can see that the common ion is at a concentration of 0.1 molar. So these two values are so far apart. There's absolutely no problem with the fact that we dropped the 2x out of this sum. All right, and that's just finishing the circle on that particular issue. Now, so going back to this, then, if we actually calculate the solubility of the individual ions for the silver, there's not going to be any change. It's 0.1 molar. And then for the chromate, we're at 9 times 10 to the minus 10th molar. All right. Now, before I close this video, there's something I want to point out, and that is that if we very quickly were to calculate the solubility of the silver and the chromate in the absence of the common ion, setting up that problem is going to look like this. It's the classic setup. All right. When we come to equilibrium, we're going to have 2x of the silver and x of the chromate. The expression is going to reduce to 4x cubed is equal to 9 times 10 to the minus 12th. And when you calculate x, the value that you're going to get is about 1.3 times 10 to the minus 4th molar for the solubility. This is the solubility of chromate, of the silver chromate solid in the absence of a common ion. So let me clarify that. I'll put the word in here. So this is absence of common ion. Now, what's the importance of this? Compare this molarity to the one that we just calculated. All right, 9 times 10 to the minus 10th is much smaller than 1.3 times 10 to the minus 4th. So what you're actually witnessing here is Le Chatelier's principle in action. And what I mean by that is that in the presence of the common ion, the shift to equilibrium that moves to the right is much smaller than it would be in the absence of the common ion, because one of the products is already present. All right, one of the products is already present. So when you're running these common ion problems, I always recommend to the student that you also calculate the solubility in the absence of the common ion, and make sure when you compare those two values that the solubility of the salt is appropriately much smaller than the solubility in the absence of the common ion, because that is a requirement because of Le Chatelier's principle. And with that